Hello, and welcome to our program, Astronomy for Everyone. For this program, we're continuing our discussion about the James Webb Telescope. And again, our guest is Tim Campbell to finish up. Now, Tim, last month we learned what the Webb can do. Just want to give them a quick rehash?
Yeah, I was going to say last month we talked about a little bit about the fact that the Webb is an infrared telescope, why it's important that it images in infrared, where it's located, the instruments that are on the Webb. If viewers missed that, they might want to go back and watch that episode. I won't go through all those details. I would like to spend more time focusing on the images and the science.
Well, sure. So what can we learn from these images from the James Webb Space Telescope?
Yeah, what can we learn indeed? All kinds of stuff. So I do have an image to start out with. This also was part of the set of first images that came out. Anyone who has seen the movie It's a Wonderful Life?
Guilty.
Yep, so there you go. This is properly called Stephan's Quintet, but this was the sort of toward the start of the movie.
Where the
angels are all talking to each other and the galaxies are blinking. These are those galaxies. So that's what this is. But I did want to point out the reason it's called Stephan's Quintet. There are 5 interacting galaxies here. I'm zooming in a little bit. There was one at the bottom that we've cut off. You can see toward the right there are 2 that are almost merged.
The ones at about the 5 o'clock position there?
Yes, and then there's one at the top, and then there's one on the left. Now, if you look at the lower right corner, I have distances, and it says 290 million light years and 40 million light years. And if you're wondering what's up with that, it's because this galaxy here is photobombing the image. That galaxy is in fact much closer to us than it is to the rest of the galaxies that you see.
So it's just a line of sight.
Yes, the other 4 galaxies are in fact interacting and they are merging. And so if we look at it, you can see some streaks going on here where there's some star-forming regions that we have in those galaxies. But also you can see this sort of wave here. This is a shock wave where gases from the galaxy on top and the galaxies on bottom are crashing into each other and heating up. And I'll go ahead and show you this image. By the way, you can see one of those, I did mention the stars. If you ever see these 6-point stars, diffraction spikes, those are stars in our galaxy, not in the distant galaxy. But watch what happens. I'm going to go ahead and show you this same thing, but this time in the mid-infrared instead of the near-infrared, as that last image was. So here we are in mid-infrared. Now you can really see the shock wave here that I called out before. But I did want to point out this. Do you see the diffraction spikes in that image?
Yes, so is that a star?
It is not a star. So this is a very interesting object. About 1 in 10 galaxies are guilty of this. This is what astronomers call a Seyfert galaxy. And it means that the black hole that we've somewhat recently in physics have discovered is at the center of pretty much every galaxy we find, a supermassive black hole. For the most part, those black holes have consumed all the matter in space within their reach, and there's nothing there. And so they're basically sleeping. They're not actively feeding. This galaxy, however, is actively feeding. It is devouring material in falling into the black hole. As that material gets closer to the black hole, but not yet inside it, it gets caught up into a vortex, spinning at incredible relativistic velocities, material crashing into other material, creating quite a bit of friction and generating quite a bit of heat. And so you get this glow of light coming off as though you are looking at a star, but it's not actually a star. When astronomers first detected these things, they didn't have telescopes that could see the galaxies. They only saw the thing that looked like the star. And when they tried to read the spectra of it, they said, this doesn't look like any star we've ever seen. And then somebody realized that the spectra of the star was actually in the signature, shifted way over to the right, where it should not be. And they said that would mean that there's a star incredibly far away in the universe, and we're still able to see light from it. What kind of star would that be? we now know that it's not a star at all. It's actually a galactic nucleus. So they call them quasars, which stands for quasi-stellar object. They still call them quasars, but if you can actually see the galaxy with the quasar, they call it a Seyfert galaxy. So that's what that is. So fun stuff there. And now I'm going to take you through a series of objects, but a little bit of background is necessary to do this. I think you recently did a show where you talked about how stars live and die.
Yeah, birth, life, and death of stars.
So yeah, and so I'm not going to go through any level of detail. Just know that it starts at, basically at the 11 o'clock position, just a cloud of dust. Clumps start to form up. Those clumps start to form into more dense nodules, which then have enough mass to start pulling in more dust, and then the next thing you know, stars are forming and planets are forming and things like that. And so that's how that happens. So there's some star formation that's occurring kind of between steps 3 and 4 in this image. And I want to go into a little tiny bit of detail on how that happens. We won't go through this in any detail. Just know that the upper left is the start of the cloud and dust. But then as you get to the next image to the right, you see this orange blobby thing in the middle of the dust. That is where matter is starting to infall into the mass that's being collected at the center. And it turns out more matter is infalling than the star can consume all at once. And so these jets of excess mass start to shoot out the top and bottom. And that continues to happen until ultimately you get a star and a solar system, some planets around it. And the reason I wanted to show you that is so that this image would then make sense. Now, when you look at this, these are called HH objects or Herbig-Haro objects. This was not taken with Webb. This was taken with a ground-based telescope, and this is what most telescopes would see, which is a whole lot of dust, and you can kind of see the jet coming out of it, but you don't really know what's going on. Let me show you what Webb sees when it looks at that same object. And there we go. Infrared light can see through dust, and we see all this stuff going on inside it. I'll go ahead and zoom in on this object a little bit for you. But this is a baby star. So stars like our sun are billions of years old. Our star is something like 5 billion years old, give or take. Some massive young stars, when we think of a star being young, we think of that star as being millions of years old. This star is not billions of years old, nor is it millions of years old. This star is thousands of years old, and it is only just forming. So this is truly an infant star. And baby stars eat pretty much the same way baby humans eat. So if anybody has a baby human, you put them in a high chair and you try and feed them. And if you want to do an interesting scientific experiment, you measure how much of the food actually makes it inside your baby human versus food that ends up in all the other places.
Hair, floor,
the floor, on the tray, on the walls, on you. They fling stuff everywhere. This is precisely what baby stars do. It's more material than the star can handle, and it just starts flinging it all over the place. So these orange jets that you see way out here in these regions, these are older emissions that came out of the spectra, or I'm sorry, out of the star as it was forming. I'll go ahead and zoom in a little bit and try and show you these little blue filaments. If I try and circle them, it's hard to see. And those are recently ejected materials. So the point is that the Webb allows us to understand these processes that are going on deep inside these nebula that no other telescope can see into, to understand how this formation is actually working.
It allows us to see through the dust and gas that we can't see invisible.
Yep. That's what it does. So a couple of more slides to just sort of set the stage for what's about to come up. When we talk about the stars come in sizes, and the size of the star during the main part of its life dictates what will happen at the end of its life. So the smallest stars down at the bottom, brown dwarfs, they just sort of fizzle out. Stars that are a little tiny bit bigger than that, our sun's nearest neighbor is a red dwarf star. They also just kind of fizzle out, but you end up with this thing called a white dwarf. It's not actually, has no more active nuclear fusion happening in the core, but it is quite hot. and it takes a long time for these to cool off. And then going a little bit bigger, stars about the size of our sun, they end their lives in the form of something called a planetary nebula. And then the really big stars, and if I go into this, the most massive ones can become either black holes or something called neutron stars that are interesting. I'll talk a little bit about neutron stars coming up. But this set of stars here is called the Harvard classification, stellar classification system. O are the biggest ones that you can actually, the rhyme that they teach, not a rhyme, but the saying that they teach astronomers to memorize this is, "Oh, be a fine girl or guy, kiss me." And when these things were originally classified, they actually were A, B, C, D, E, F, G. Once we understood what they were, we discovered that the ones called O happened to be the biggest, so they moved it to the front. But they didn't re-letter them. So that's why you see this crazy out-of-order sequence when we put them in order. Only the biggest stars can become supernova or neutron stars. Everything else has a less spectacular ending. And with that, we'll get into examples of them. So here's the first example. This is what happens to stars like our sun. And so this is actually the Ring Nebula. A lot of amateur astronomers here in the Northern Hemisphere have seen this object. When you look inside it, and you can see as we move in, there is a dead star in the very center of the nebula, and it has expelled most of its material going off into space after it underwent some collapse. So the star swells up, gets really big, and then at the end it sort of collapses down and it sheds off this gas, slowly going out. Now this is quite large. If you look at the white dot in the center of the image there, our entire solar system, from that white dot to, say, Pluto, which we demoted, now a dwarf planet, would only be about a pixel or two. So this is actually quite big. I think this is about 1.3 to 1.5 million, I'm sorry, 1.3 to 1.5 light years across. So it's quite a large distance involved. We can also look at it also in the mid-infrared, and we see these rays coming through the gaps, and we believe that these are like corpuscular rays of sunlight shining through clouds, that's going on, and the radiation of the star in the core is basically causing those gases to glow, causing this very spectacular image.
We're going to take a quick break. If you have a question, please send us an email. The address, of course, is down at the bottom of your screen. And coming up next is Term of the Month with Stephen.
Thanks, Don. The term of the month is occultation. An occultation is when a relatively nearby object, say an asteroid, blocks part or all of the light from a distant bright object, such as a star or a large solar system object. If several telescopes are used, then the shape and size of an occulted object may be determined. An idea for finding the currently undiscovered Planet 9 has been published. Due to the alignment of several trans-Neptunian objects, an orbital path has been calculated. The idea is to use 200 40-centimeter, that's 16-inch diameter, automated telescopes that are separated by 5 kilometers, that's 3 miles, operated for 10 years and aimed around the expected orbital path. By the way, 200 telescopes 3 miles apart is 600 miles. It's a straight line of telescopes. Anyway, this should be able to detect occultations of trans-Neptunian objects due to main belt asteroids. Computer studies for such a system show high sensitivity to a 5 Earth-massed object, like Planet 9, out to 800 astronomical units for 90% of potential sky locations. It's likely to detect 1,800 trans-Neptunian occultations, providing shape, size, and albedo information. It would also measure the Yarkovsky effect, mass and mutual gravitation deflection of main belt asteroids occulting Gaia catalog stars. And it would only cost $15 million. That's the term of the month, occultation. Back to you, Don.
Thanks, Stephen. We're back with our guest, Tim Campbell, talking about all the pretty pictures that the James Webb Space Telescope has taken. So where do we go to next, Tim?
All right, so we left off talking about all the different ways that stars can end their lives. And so we started with an example of what happens to a sun-like star, but let's show an example of what happens to some of the more massive stars, the O and maybe the largest of the B-class stars. So the object here that I'm showing you, this happens to be an image that was captured by the Hubble Space Telescope. There are many amateur astronomers who have also taken similar images of it. This is a supernova remnant. So this is what happens to a really large massive star when it dies. In 1054 AD is when the star that created this nebula exploded. We know this because Chinese astronomers documented it quite well. We also found paintings in the American Southwest that Native Americans painted depicting how they had actually seen it. It would have been quite bright in the sky to pick this up.
I believe it was even visible during the day for a period.
Yes. I'm told that it probably put out about as much light as the full moon, and you can of course see the full moon during the day. So that's what caused it to appear. But let me show you what happens when Webb takes a look at it. So here now is the Webb image of the very same object. I'm going to go ahead and zoom in on the center of this so you can see something interesting that's going on here. And what I want to call your attention to is these swirls that are sort of here going around the center that you can see. This swirly stuff is what we refer to as cyclotron radiation. So in Chicago, we have Fermilab. In Switzerland, we have CERN, and they have these particle accelerators. That's a cyclotron. You're accelerating something to as close to the speed of light as you possibly can, and you're thinking, well, how does that happen? Why would something like that happen? Well, the thing to keep in mind is that a neutron star is what happens when a star is almost, but not quite big enough to end its life in the form of a black hole. But you're really, really close to becoming a black hole. You're almost there on the mass. And so in the same way that you realize that black holes can really pull in matter and accelerate it to absolutely fantastic speeds, neutron stars can do that too. Not quite as fast as a black hole, but pretty close to it. And so this is material that's being accelerated to incredible speed and causing it to glow, and we can detect this in radio telescopes, but we can also detect it in the infrared in the James Webb. It's able to see that. That image, by the way, does show up slightly in the Hubble. It's hard to see, but it's really obvious to see in the Webb. So here's another image comparison between Hubble and Webb. This is taken in visible light with the Hubble, so this is Galaxy NGC. NGC stands for New Galactic Catalog. It's just the name of the catalog, 628. It's the 628th object in the catalog. And you can see the distance is 32 million light years away, but it's taken in visible light. And while it is pretty, we can see lots of red spots around it. Those are star formation happening in this galaxy. But let me show you what happens when we switch this to what Webb sees. So this is a combined result of both the near infrared and the mid infrared at the same time. And you see
both from James Webb.
Both from the Webb. But we've merged the image data together to create one image. And when we do that, first of all, the dust disappears, so you can see through the galaxy. You can see all these stars close to the center where the massive black hole would be located, and we can actually see those stars in this image. We could not see that in the Hubble image at all. So this helps us to explore more about what's going on in the galactic core. There's something else that I really want to point out here. This spot here. If you look at that spot that I've just circled, there is this nice, neat hole punched into the disk of the galaxy that you really don't see such a perfect circle anywhere else. What we believe happened there is that a supernova explosion, a star, went off as a supernova and blew away all the material away from that part of space, leaving a hole in the galaxy. Now, when we go back to the Hubble view of the same image, you'll see that it becomes milky, and you really don't see, I mean, you kind of see a little bit of the tracings of it.
Once you know it's there,
yes,
it's more obvious.
Then it's more obvious. So again, the reasons for using the infrared and what the Webb can do is it's allowing us to get a whole lot of information that we couldn't see any other way. This is a very recent, I think this image is only maybe a month old, maybe two. This is an object called Westerland 1. This is an open cluster that's in the Milky Way galaxy, but this is a very special type of open cluster called a supercluster. There are not many of these. This happens to be the most recently discovered one. It was discovered, I want to say, 1961, and it also happens to be the closest one to us. But what is fantastic, and the reason that it's called a supercluster, is the incredible number of O and B class very, very large stars. This is exceptionally rare to have something like this. Largest stars don't live very long, and so these these stars live only for millions of years rather than billions of years, like stars like our sun. So this cluster site, we suspect over roughly the next 30 million years or so, maybe 40 million, will probably produce something like 1,500 supernova explosions. So this is extremely fascinating to astronomers because of what they can learn about the lives of these stars at that scale. We don't have many other locations where we can find such richness to explore like this. There is a star here that I do want to talk about called a magnetar. So one of these stars is a magnetar. A magnetar is no longer active. It's a dead star, and it's basically a neutron star. Now, the reason we call these things neutron stars is in a normal star, it's mostly hydrogen gas, and when you have a hydrogen atom, you've got one proton in the nucleus and one electron in this electron shell, zipping around the nucleus. The electron never goes down into the nucleus. They don't get together due to something called electron degeneracy pressure. And this is a force, but every force has its limits. And so in a neutron star, the force of gravity is so unbelievably powerful that it overpowers even the electron degeneracy pressure, forcing the electron into the nucleus of the atom, and they get together and essentially form sort of a synthetic form of a neutron. It's not a normal neutron like most atoms would have because of the force of gravity. But in the case of a magnetar, these forces are so unbelievably powerful that it creates this incredible magnetic field. And the magnetic field is so strong that if we had a neutron star that passed, say, half the distance between the Earth and the Moon, at that distance, all magnetic recording media on the planet would be wiped instantly. So every credit card would be wiped, every recording tape, every hard drive on every computer, all instantly wiped because the field would be that strong. If you got within 1,000 miles of this intense magnetic field, it would end your life in the most interesting way. You wouldn't have to worry about burning up because the electromagnetism is so powerful. The forces that hold two atoms together to create molecules is essentially electromagnetism. This star overpowers that. So essentially all molecules just fall apart. So every molecule in your body ripped apart. In fact, electrons ripped off of the atoms from the strength of this magnetic field. So incredibly, incredibly powerful things called magnetars, and there's one of them there.
In a couple of minutes that we have left, Tim, what else have you got there?
All right, so let me show you another. This is a Where's Waldo image. These are called transients. So the Webb goes around the sun. We snap an image of a piece of the sky. We wait another year. Webb goes around the sun. We snap the image again of the same piece of the sky. And then we say, did anything change? So in this image, something in fact did change. Each one of these is a galaxy that we've really zoomed in on, and there's something different. It's hard to tell the top from the bottom. I ask audiences if they can pick it out. Every so often somebody gets one, but mostly they don't. So I'll go ahead and do the reveal. And you can see that in the 2022 images, that's the top row, nothing was in the upper image, but the lower image, there's a new spot that showed up. That's a supernova explosion. And then the middle image, also again, bottom, there's another supernova. The top image on the third row has another supernova. These are very difficult to find, and most telescopes struggle to find these things. Very few distant supernova explosions with a redshift with a Z value that corresponds greater than 2. have been found by other telescopes. Here's one image taken by the Webb 1 year and then the next year, and look at this. Everything that I just circled is another example of one of those transients if we were to zoom on it. There are 80 of those circles in just one image. So with just one image, Webb has already outperformed the collective science of all the other telescopes combined. And that is the marvelous technology that the Webb is making available to astronomers.
This telescope is truly amazing. Again, we could go on for hours.
We could.
Yeah, but we can't. We've got time limits, unfortunately. So, Tim, I do want to thank you for coming on the show to let our visitors know about the wonderful things of the James Webb Space Telescope. Please visit the club website. The address is down at the bottom of your screen. And also, if you didn't see the December show, go back and see it, and that'll help you understand this show just a little bit better. And coming up to close us out is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for January 2025? We just had the solstice in December on the 21st, and so the days are changing length. They're getting longer in the northern hemisphere and shorter in the southern hemisphere, but the changes are slow near the solstice, and they speed up by the equinox. So in January, it's slow. January starts on the 6th with a first quarter moon. It's full moon on the 13th, third quarter on the 21st, and new moon on the 29th of January. We have Mercury shown on the 1st of January at sunrise. Mercury goes from Ophiuchus to Capricornus, and it rises an hour and a half before sunrise to about sunrise by the end of the month. So it's obviously better at the beginning of the month. Then we have Mars, Jupiter, Uranus, Neptune, Venus, and Saturn shown here on the 19th at approximately sunset. Mars goes from Cancer to Gemini. There is a Mars opposition on the 15th of January, so pretty much Mars is up all night in January. Jupiter is in Taurus. It sets from 2 hours before sunrise to 4 hours before sunrise. Uranus is in Aries, and it sets from 3 hours before to 5 hours before sunrise. Neptune is in Pisces and sets 6 hours after sunset to 4 hours after sunset. That's in the northern hemisphere where the nights are shorter, or nights are longer. Saturn is in Aquarius and sets from 5 hours after sunset to 3 hours after sunset. Venus is in Aquarius and goes to Pisces by the end of the month, and it sets at 4 hours after sunset pretty much the whole month. Venus has maximum eastern elongation on the 9th, and so it's farthest degree-wise, angle-wise from the sun on that day. Pluto is in Capricornus and has superior conjunction on the 21st. There is no way that you're going to want to look at Pluto in January. And that's what's up in the night sky for January 2025. Remember, we don't charge money for this show, but we may tax your brain.